Welcome back, guys. We're looking at more calculus review. This time we're looking at chapter 4.2, and let's just go. Oops. Here we go. 4.2. Let f of x be a continuous function satisfying this beast of an equation, really, containing the points negative 1/2, 1/2, negative 2, 2, and 2, 4. Find an expression of dy dx in terms of x and y. Okay, so here's our challenge. Let's copy this down over here. X to the fifth plus x to the fourth y minus x y squared minus y cubed equals 0. So clearly we're doing some implicit differentiation here. And remember that the idea is that if you take the derivative with respect to x of some function in terms of y, that's going to be the derivative in terms of y multiplied by dy dx. Okay? So maybe I should write it like this, is equal to du, why did I write that? Du dy multiplied by dy dx. And don't you just feel like canceling out those dy's and making that du dx? That's kind of the idea. So that's going to be our guiding principle here. This is going to be the derivative with respect to x of x to the fifth, and we're going to be doing this really slow, plus the derivative with respect to x of x to the fourth y, minus the derivative with respect to x of x y squared, minus the derivative with respect to x of y cubed, and that's equal to the derivative with respect to x of 0, which as we know is just 0. So our very first term, no problem, that is 5x to the fourth. I can deal with that. The second expression, this is going to be a product rule because we have x to the fourth multiplied by y. So it's going to be the derivative of that first function, which is x, 4x cubed multiplied by y, plus the derivative of y multiplied by that first function in the pair. So the derivative of y is dy dx multiplied by x to the fourth. See how this is going? Minus, this is another product pair. So it's the derivative of x, which is 1, multiplied by y squared, plus the derivative of y squared, okay. The derivative of the square of any function is 2 times the function to the first power, multiplied by the derivative of that function, dy dx. All right, let's put a couple multiplication dots here, and then multiply that by x. Minus, now the derivative of any function cubed is 3 times that function squared multiplied by the derivative of that function with respect to x equals 0. Let's open up some of those grouping symbols and let's turn our dy dx into y prime. That'll make it a little bit easier to write all of this. All right, so our next line here is 5x to the fourth plus 4x cubed y plus x to the fourth y prime minus y squared minus 2 y and then y prime again. Actually, we've got an x. So 2 xy y prime minus 3y squared y prime, and that's equal to 0. Let's take everything that doesn't have a y prime and shove it to the left side of the equation. I trust your algebra is sufficient for me to just, well, first of all, take all of these terms that have a y prime, x to the fourth y prime. This is negative 2xy y prime minus 3y squared y prime. And then we're going to take all the other terms that do not have a y prime, and we're going to put it on the right side. So are any of these? Yeah, I think I can start with this one, y squared, and then minus 5x to the fourth, and then minus 4x cubed y. On the left side, you're going to factor a y prime. So we're just basically going to cancel it out of the expression. X to the fourth minus 2xy minus 3y squared. Factored out that y prime. And then now we're just going to divide by that x to the fourth expression, giving us the answer. Y prime equals big fraction bar y squared minus 5x to the fourth plus 4x cubed y, everything on top of x to the fourth minus 2xy minus 3y squared. Great! You've got your expression for dy dx. Next, you're going to evaluate that dy dx at all of those places. Maybe we'll do the first one together, and then I will go ahead and, how do I say this? Let you guys do the rest of these. So let's do this first one together. With my calculator, I want to store those values of negative 1/2 and 1/2. So I'm going to put the x coordinate in the store value a. So negative 0.5, I want to store that as letter A. Okay. This is why your calculator has those letters. It's not so you can send notes to each other in class. It's so that you can store values in them. Likewise, I'm going to store 0.5 into B. Okay. Now I'm going to go ahead and I'm just going to use A and B to evaluate this function. Now this gets a lot easier if you actually have a fraction bar here, and we do. So go ahead and type this out. Look how much nicer that looks. And you also have the added value that you can reuse this equation for letters B and C just by storing new values into A and B. So hint on how to do those next two really quickly. I'm going to push enter. We're getting 1.666, which is 1 2/3, and if my math serves me correct, that's 2/3. Did I say 2/3? 5/3. So we got 5/3 here. Oh, it'd help if I turn on the pen. 5/3. Go ahead and do the rest of these and check back here in a minute. Whoa, I'm so sorry. I noticed I made a mistake here. This is not in the numerator. This is not plus 4x cubed y. That's minus 4x cubed y. So this is y squared minus 5x to the fourth, and then minus 4x cubed y. Boy, it's lucky I did this calculation the way I did, because now I can just go back to this previous calculation and go up and make this a minus. That's pretty painless, right? Oh, what answer? Oh, I got -1. There you go, -1. Keep working. Okay, so next we have this factorization of that same polynomial, and we're supposed to use it to graph the function described earlier. So we know that this is equal to 0. And we also know that we go through the points -1/2, 1/2, which is right here, -2, 2, which is right here, and then 2, 4, which is right here. So here's what I'm going to say. If we know that this is equal to 0, then one or the other ones of these three factors has to equal 0 as well. That's the zero product theorem. So let's imagine that the first factor here, x plus y is equal to 0. What would that look like? Well, if x plus y equals 0, that's basically it is a diagonal line with a negative slope of, or slope of -1. So let's just draw that over there. And notice that well, first of all, notice that I can't draw a line. Second of all, notice that it does go through two of the points over here. The next factor over here, actually, that's never equal to 0. So we don't have to worry about that. The last factor over here, x squared minus y, if we make that equal to 0, that turns into y equals x squared, which is just a parabola. Let's graph the parabola real quick. I think I put that 1 point in the wrong place. It should be 2, 4. 2 and 4 is way up here, right? Okay. Yeah, I think I'll use green, and we should go through 1, 1. We should go through 1, 1 again, and then -2, 4. Notice how those two lines overlap with each other, right? What does this mean? Well, this means that we have one point, at this one point where they intersect, 0, 0, there's like a decision thing goes on, that has to go on. And the question is, for negative values of x, are we on the blue line or are we on the green line? And then for positive values of x, are we on the blue line or are we on the green line? Clearly, for negative values of x, the graph that fits it the best would be the blue line. So we'll just get rid of all of that green line on the negative side of the axis. How about on the positive side, where x is greater than 0? Do you think we should use the green line or the blue line? Well, yeah, we have evidence that the solution curve is going to go through the green line, since 2, 4 is a solution for y equals x squared, but not on the graph of y equals -x. So let's get rid of all of this because we don't have evidence for that. And this is what our graph looks like, or at least that's the best estimation of the graph that we can draw. Okay. No, you don't have to worry about graphing these kinds of functions in AP Calculus. It's not really part of the curriculum, but it is an interesting thing to look at. This wouldn't have been possible unless we had a couple of different initial values to help us along here. All right? Let's look at number 4. Can the expression you wrote in number 1 be used to define or to find x, dy dx at x equals 0? And that answer is a big fat no, because we would get a 0 denominator. Because dy dx is undefined at 0, 0. Just scroll up and look at that function. You'll see that denominator is going to equal 0. Okay, let's see. Evaluate from the left and the right, and that expression right here, I'll highlight that. These are all expressions of the derivative evaluated at 0. So this is saying what is the derivative from the left and what is the derivative from the right. Looking at this graph, from the left, we are following along the blue curve, which has a slope of negative 1. So as we get closer and closer to 0, 0 from the left side, our slope is staying negative 1. Now on the right side, we're following the parabola. And if we know about the parabola, there is a horizontal tangent line right at the vertex. So here, on the right side, the slope is approaching 0 because, well, it's a parabola. So can we evaluate that? No. Why? Because the limit from the left and the limit from the right is not equal to each other. So we'll just say the limit as x approaches 0 from the left of that expression, and I'll write it out ahead of time. There we go. The derivative definition, the limit definition of the derivative from the left is not equal to the limit definition of the derivative from the right. So the derivative does not exist at x equals 0. So we have these two. We should read along here. We have yet to discuss the calculus of exponential and logarithmic functions. Yes, we have, actually, because this is the end of the course. However, a sense of their differentiation could be developed geometrically. Take a look at the two exponential functions, 2 to the x and 3 to the x. Imagine a sketch of the derivative curves. Okay, the derivatives for both of these functions would always be positive. From the left, on the left side, the derivative is approaching 0, and on the right side, the derivative is approaching positive infinity. But wait a minute, these graphs approach 0 from the left side, or on the left end, and they go to infinity on the right end. So really the graph of the derivative and the graph of the function kind of look the same. Let's just keep reading. Precise values of the derivative are still open to interpretation with this technique. So it may appear that the graphs of 2 to the x and 3 to the x are much like the curves themselves. In fact, the derivative of 2 to the x is a product of 2 to the x and some constant 0.693. Putting the x there does not make this more clear. And then the derivative of 3 to the x is the product of 3 to the x and 1.09. So we can imagine that there is an exponential function where the derivative is the function itself, some number to the x power, multiplied by 1. So basically the function is its own derivative. And based on what we see, since this one, that the multiplier is less than 0, and in this one the multiplier is greater than 0, we know that the number the base, I should say, the base of the exponential function whose derivative is equal to itself should be a number between 2 and 3. Okay. In fact, we know what number that is. That number is actually E. And E, as you'll remember, is 2.71828, approximately. So cite an example previously studied of a function whose derivative is equal to itself. Yeah, we know what that is. It's y equals e to the x, which is, by the way, 2.71828182845 to the x power. Okay? And that kind of fits the hypothesis. So there we have it, everyone. That's our section 4.2 review. Hopefully you enjoyed that, and I'll see you next time.